So those that are still with us, you got to get to the end. You got to sit through some guy talking about uncertainty and whatnot till then, and E74 and all the other stuff. I get questions on load cell simulators. I texted this to the people who had asked. There is the article. Our blog post has lots of topics on this. Here's a budget simulator. If you have a meter and you don't need to calibrate in accordance following the standard, this thing works very well. I recommend it. It won't break the bank. It's very accurate, very easy to use. It's it's a board with a bunch of resistors soldered to it and at such set points, and they're trimmed in. Other than that, we are working with Ohm's Lab, and we have a higher one if you want. Someone was asking about meters. Just shoot an email over or whatever. We have 3 coming in from Ohm's Labs that are precision resistors and all the bells and whistles to calibrate meters. Have a first force point simulated load that's allows you to do low points, because what ASTM says, the caveat, and there's a sort of simulator cal, the and I think our new simulators will go down to O2. What ASTM basically says is when you do substitution, you have to do the full range. So this limits you, and that's what I'm explaining. In some out here, it's about 4,500, but yeah, and 600 for the pretty cheap one. But ASTM has specific guidance in it regarding simulator calibration and what you need to do, and why this wouldn't work for ASTM is because if you had a 2 millivolt, 1,000-pound cell, half a millivolt is what, 250 pounds, and most people want to use it below that. So going down to that O2 value, at least 0.2 gets you 10%, O2 gets you 1%. So that's where, and that's tricky. It's star bridge pattern, and there's a lot of other stuff. Also have paper on it if you go to the documentation and tools. So I did send the blog links. I wanted to answer that question as we're coming back, as people are taking their bio breaks and whatnot. So this is it. Lots of stuff to look at, and what we'll look at here. We already covered mass to force, but we'll look at the hardness of adapters. Some stuff I made some reference to, and then this is again for those people that are new. We did talk about some of it. Just there's things you just want to make sure that you're keeping things minimized, and that you don't want to you want to keep centric, which is our little happy face over there, and you want to avoid side load, eccentric forces, or torque forces. And torque forces especially can cause damage to the sensor depending on how it's made and all of that. So really we want our happy face over here, and we want to facilitate that with adapters. We've had some like button load cells and the others. So there's side load, any load acting 90 degrees, and eccentric load. And we talked about that earlier. And then again, actual load line, another repeat slide, eccentric forces. We talked earlier when I talked about multi-axis load cells. We said a load pad can be used, surfaces should be ground flat. Large deviations by using non-flat beat up pads. Tension, we want adapters, we want a spherical radius. Misalignment, most of our machines demonstrate bending of less than 2%. Also specify this error. The use of proper cal is required to minimize this error, and you keep going on and on. There's that picture. Here's the spec sheet. What we're looking at this is that side load sensitivity. I had pulled that out when we were showing the uncertainty, but you look at this number here when you put it in a cal machine, and those other documents made reference to that. So types of load cells. Again, that S-beam that was off center, that uncertainty really ballooned on us, where if we misaligned a shear web load cell, it wasn't nearly as bad. So there's a story on here, and I was the one doing the calibration. The customer had a 1,000,000-pound load cell, and I just got numbers that were about, it was 1490 higher, but the numbers were about 1,500 pounds higher than the previous calibration. So what our techs typically do, which is good practice, is once you get a cell in, you look at the old data. I mean, some people say don't. Look at the old data. Look at if there's 3 years worth of data, and I just took some numbers. I'm gonna look back and see if anything's trending, if anything looks weird or whatever. And on this load cell, I knew, I kept digging, and I'm like, wow, this load cell's pretty stable. I'm expecting, like, I wouldn't have questioned like 250 pounds out of a million, maybe even 500 pounds out of a million. Though on this load cell, all of a sudden I see a 1,500-pound shift. And you start and you said, hey, is this a stability? Did things change? It's an old load cell. Did they switch the cable? No, because that's something. 4 versus 6 wires, certainly something. What happened along the way? Why is this all of a sudden changing, that the history is such? So call the customer, and they inform me, oh, I had new top blocks made that I sent with the load cell that I've been using the last 3 months. And I said, well, the guy's name was Lane. I said, what do you want to do with this? Like, you got to switch in your data. It's high. The history shows it shouldn't be this high. He goes, I'll send you the old blocks. Let's see what we get with them. So he sent in the old blocks, redid the test, and now the load cell's reading about 180 pounds out, which fully expected to read 180 pounds out. We look at all of this and the customer determined, I'm just going to use my old adapters. I don't need the new ones. The old ones weren't that worn. I figured I was just going to buy them. Fine. I said, okay, and we can adjust it. We can do whatever you want. So just looking at this, old versus new adapters, that no one thought anything of changing adapters into the cal cycle and what it would do. If you look at this number, this individual contributors, this number is pretty high, right? Accreditation number, stability of reference standard, all that stuff. What ended up happening is, if you looked at everything, the expanded uncertainty that he had when we started calculating everything, 269 pounds would have changed to 1,490 using his new adapter. So basically almost a 6x, just because of the difference in hardness of the adapter. This is that take note, whether you're field, reference, whatever, these top adapters that are used with the majority of load cells, not all of them, it can impact the results significantly, because different amounts of hardness, and I'll show that in a slide, are going to affect the strain on the load cell. And here's a test that I did. This is the reds, obviously the top adapter. I had this cell for like a week. 4340, that's a steel, hardened top block, and it wasn't super hard. Sometimes people ask, maybe like a RC of 42. So looking at these differences, and I did this the same day, I did different days, I did over the weekend, I did all this, and at the end of all this, I could say, undoubtedly, this setup right here, with the customer did not send their blocks, we used something softer not to indent the load cell, versus using a hardened adapter, the difference was on this specific load cell about 0.3, about 0.25, you see right there, 0.26 to 0.307%, just from swapping top blocks. It happens all of the time. People send us stuff without their adapters. I'm sure they're sending you stuff without adapters, and you're giving them results, and the results are only valid if they're using the same hardness of material that your adapters are, if they haven't sent theirs. So we modeled this. You can model it in SolidWorks. This is SolidWorks. It's modeled in, and you can start seeing the loading block. And what what impact does this have? This modeling 2% difference in the strain of the gauge between the hard and soft loading block is what you calculated out using, as I said, SolidWorks. Materials with different hardness experience different amounts of lateral deflection under the same amount of load. Therefore, the varying hardness causes different amounts of stress between the block and the load cell. So above, we tested steel to steel. It gets much worse if we use softer material. One of the field guys came in, was doing a testing machine, came in, he said he was in the area, gave us a call. He said, can I come over? I'm doing something and my numbers, this machine's been in for 10 years and my numbers are not showing this machine is in. And he brought in his block, and here he had a ground piece of aluminum. So yeah, his numbers were way out. And when we used another adapter that he had in his case, the numbers were way in. And he saw this, and he was a British gentleman. That's where he said aluminum, and it kind of stuck with me. Though it makes a major impact. So the easiest thing to do is to marry those load cells. If you're going to buy high capacity load cells, ISO is not wrong. And when I say ISO, I mean ISO 376 is not wrong in that annex about recommending adapters and keeping them with the load cell, because you avoid these errors awfully quick. And the last thing you want to do is to be out in the field or in the Cal lab is adjusting machines that you're adjusting because you switched a top block or something like that. So do all cells react the same way? No, I've done numerous tests on these shear web cells and they don't. The difference, you can see soft block, we used an Agilent 3458A with this one, but look, hard block, soft block, one count at 10,000. I can't discern these numbers. Our machine's only good. This is our 100K. It's 0016. I don't expect the load cell. Typically, load cells are about 7 to 10 parts per million when I do these, that I can discern. Anything less than 001, I got to throw that number out and say there's no difference because I can't tell. 002, yeah, our machine's 016. There might be a hair, but it's 10,000. So no, regardless, I can say on the shear web load cell, I'm not seeing anything that makes a difference. Now, I have not tested aluminum to like a super, hardness scale. So no, we basically did, okay, soft block, something that's gonna yield a little bit versus a hard block, and the difference is nothing. You take a multi-column cell, a single column cell, and do the same thing, you're going to find a noticeable difference in the gauge. It's just how things are made. We covered this one earlier where people like to pull out the adapter, and someone achieves, you saw our uncertainty budgets and some of the other stuff. Say you achieve O2 at that 20% point, and then you pull this adapter out. Well, you're not going to get it anymore, because even if you put this adapter back in to get it exactly where it was, there's going to be a difference, and it's going to require calibration depending on where you are and where you need to be. If you take it out and put it back in, we get very, very close. So also reproducibility, these adapters here, reproducibility of the load cell gets so much better. When I do a 2.5-day course, we play with these, take them out, do all kinds of different things. So solutions here, this is bad. This piece here, we see a lot of these cells come into our lab. I would like within the next 5 years to not see any of those come in and see people start implementing policies to say, okay, I'm going to send you my adapters so you can thread it exactly the same amount that I do. However, if you send in a compression adapter and it's tension and compression, tension has the same exact error. So it's just so much better to lock an adapter and do away with this. Buy it up front with the adapter. Shame on some load cell manufacturers that don't push this, because someone just goes, okay, I'll buy this, and then they get the cell. Just, you can always get them. And guess what? If you buy it with the adapter, we trim them in with that adapter in. There's some little polishing that goes on and everything else. Your cell gets so much better overall than if you don't buy it. It's so that should be a takeaway. What about different load cells? We talk about shear web load cells. There's so many load cells out there, right, that have different thread depths and everything else. Are they going to increase or decrease the amount of strain? Well, most things that have a hole, depending on the thread length uh, and the engagement, are going to change. So this is a Sensitech, decent load cell by all means. Customer sent this in, and they basically didn't want to send their adapters. I said, "You have them?" "Yeah, I have them." I said, "Will you send them?" He's like, "Just tell me what you did. I'll replicate it." The guy's pretty proficient and has machine shops in the area, so I knew he was going to replicate it anyway. But I'm like, okay, this cell came in. I'm going to do a test. And basically, I do this test with different adapters. I thread one in, pretty extreme, one into an inch and a half. The actual thread size on the load cell was inch and a half. So yeah, inch and a half, inch and a half, and then the other one with half-inch engagement. They sent this in using a gauge buster, so it was direct read. And when I applied 10,000 pounds between the different adapters multiple times, I got anywhere from 10,000 1.5 with the inch and a half, plus or minus maybe 3 pounds, to that 942.3 plus or minus like that 3 pounds with the half-inch adapter. So difference on a 10,000 pound load cell of 59.2 pounds. And if we look at this graphically, you can say, okay, I want to be within 0.25%. Funny, TUR, people get TUR didn't change. That's test uncertainty ratio. That's basically the ratio of what the required accuracy to what you're calibrating. We were targeting 25 plus or minus 25 pounds. We were doing this with a really, really low uncertainty of about 0.6, 0.6 for K equals 2. And look at this graphically. I mean, this looks nice. You're well within. You have lots of room to be within, right? And then use this other adapter. There's where nominal is. The red points are my control limits. People might know that. I want to be within these two red lines, and I'm nowhere in. So I make my little stupid asinine comment here is, what is the probability of the measurement being within 0.25 if the top adapter, that threaded adapter, is changed out? And then my stupid point, and I have a friend from Hell, Michigan. I said when hell freezes over, but it does freeze over in Michigan. But anyway, it does not freeze over in Caymans. You can go you can go to hell in the Cayman Islands, and I can guarantee that won't freeze over. So just things to be aware of. If people don't send adapters in, what's good practice? What do you do? The best practice is to ask them what they're doing. So the discussion here is basically, how should we handle? If we don't know, what should we do? Right? How would you handle the problem with a customer load cell? Right? Think about it. So as you're thinking about it, there it is. Try to get some engagement back. I know it's afternoon, a lot of information, uh, lots and lots. So I estimate that our number, we were getting pretty good participation in maybe the 70s, and I estimate that number is going to go down because it's afternoon. And but okay, so as we're doing that, and I appreciate the slide, I do have a question. With a shear web load cell like the one on slide 178, as everybody's answering that, is there no way to mitigate the error when you have to change the top adapter for Cal? That's an excellent question. I should have talked. I don't like saying this. There is a way to mitigate the error. And that would be, you have something that you lock in, and you have the same thread depth. It's a pain because for tension, you would have to, you really have to engage it. Like, so if I have a 5/8 18 thread, I might say, if I'm consistent and I engage 5/8 18 and I thread it on the shoulder, and for tension, I have like an eye bolt and I engage that 5/8 18 and tighten down the bolt, I can mitigate the error. It's a bit difficult to do and get it right. I can get that error down to about 0.01% if I do that. If I'm consistent, if I decide I just want to thread it in an inch, the problem is what's a nominal inch. So I'm going to have some variation with that. But if I say, okay, my compression adapter, I'm going to thread it in an inch. It's got a spherical surface, and then tension adapter, I'm going to thread it in an inch and I'm going to lock it down. You can mitigate that error. Tension, more so, it pulls away, but you can mitigate it. The best thing is just to lock it into place, or if you really need to, that the budget cell is going to give you that one, because there's all that meat in the center. There's so much more material, is going to be the better choice if you have to change things out. So hey, awesome, we got 65% voted, and we'll share this. Maybe we'll get one more to take us up to someone coming back and want to do that. But yeah, okay, 65. That's not bad for afternoon. Thank you all for staying with me here. So I don't think we're going to get another one. And I got to share these polls. So you see, call the customer and get more information on use. Yes, there's two things you can really do, jokingly, on that. Yeah, no one's saying report your customer to your accreditation body. That's good. We don't really want to get into that. We want to get into the more education mode than anything else. So my original slide here said hire an attorney and some other stuff, but I changed the poll a little bit. So you get choice number one. 97% of the people said call the customer and get more information. Another, I think two people said calibrate it and document what you did. Both are not bad. Calling the customer is obviously the better solution. What happens, the caveat to this is, what happens when you're the Cal Lab and you're dealing with a third party that won't get to the customer? They're third partying and they're sourcing all the stuff out because they want the one central point and they can't get you an answer. What happens when you're dealing with a purchasing department that you can't get to the end user? So in that situation, the documenting it is your next best thing. We like to educate, probably over-educate at some point. I don't think there's such a thing. But at the same time, it's like if you can't get through to somebody, you only have infinite amount of time on Earth probably, and you're going to have to move on at some point. So basically, putting a note on the cert is like, look, note, in compression, the adapter was threaded tight against the top of the load cell. An adapter used by Morehouse Instrument was threaded approximately. And there are weasel words in here. And I use weasel words because good auditors will get you on this. And when I kind of danced around the 0.01% with mitigating that risk, it's like, yeah, well, how much do I torque it in? What all the extent I need to go to things? So approximately, which means we're not going to get audited for our dimensional measurement on how good our 1.5 inches, because we didn't report the uncertainty of plus or minus 0.001 inches or whatever. So we're kind of doing the best we can. And then zero return values we're taking after the 30 seconds after the load was released. But yeah, so kudos to everybody. Calling the customer, ask for adapters, contract review. This customer actually told us what they wanted to do, and we documented it, because we don't want it coming back that they say, oh, I only use this, or my adapters don't match. We're working now to get much better at documenting all of this stuff on the certs, and there's so many when you get into this field. So many things you can put on that cert, and at some point you question how many people are reading it and what's the value, but that does not matter. If you can provide it, it makes it so much easier when that phone rings and says, I'm not getting the same results. We had a situation where that was exactly what was happening. Your lab did this, I did it in my lab, I sent it down to my lab and they got the same results as my lab, and now your lab is different. I said, I said directly to the customer, I said, what do you have? He said, I got a 5/8 whatever, looked at notes, and I said, do me a favor. How far in are you? And I'm going 3/4 inches. I said, well, our note says we use this adapter, threaded in threaded in 10 turns. 5/8, 18, 10 turns is 5/8. Thread your adapter in 10 turns. Can you do that? Yep. Got a call back. I said, so what are the results? We match you perfectly now. Okay. Ideally, we would have locked something in place at the 1.1 or 1.08 inches, though this was the next best thing. So on this cell, it was 1.5 inches. On that customer's cell, it was 5/8. If we don't have the known adapter that the customer is using, we typically will thread it in the thread size. And the engineering, if you look at strength of materials and everything else, the first 3 threads carry the majority of the force. And after that, you're not really posing a safety risk. So if you have an 1.5 diameter, depending on what capacity you're going to, if it's designed right, but if it's an 1.5 and you thread in an 1.5, chances are you're not losing anything as opposed to threading in 1.6 inches, anything significant. That being said, because all that strength is in those first few threads. This one, not as big of a deal for different results, but we find this is one of the harder ones for us to grab in the lab. And that means for customers to tell us. Now, the assumption is, and nothing wrong with some of our competitors, but most of our competitors do the cal this way. So I'll put a C here, if that makes sense, or whatever this arrow keeps happening to me. They do it this way. Morehouse, what we find is when we start asking customers, the majority, when they have a cell like this, load flat. Our competitors do it because they can change tension compression in the same setup, and a cal takes 20 minutes, which takes us 2 hours. Am I salty about that? A little bit, so I'll stop talking about it. But in any case, is there a difference? And how do you ask the customer? Do you load it through the bottom threads? What thread? So this is very repeatable, and you can quantify this error. You can go talk to almost any manufacturer of shear web load cells and ask them about loading through the bottom threads, and they're all going to give you the same answer that yes, there is a difference, and that difference is somewhere around 0.01%, somewhere around there. This one, luckily, I had the instrument that I was testing with for this case that you got the slide for, 25,000 pound load cell. The difference was 3, that's 0012. If my resolution were better than 0.5, maybe that was 2.9, maybe it was 2.8. Typically, we see about 0.1. That's what happens. You can kind of account for it. I don't know if you want to correct for it because it's a little variable. The easiest thing is just to ask the customer and try to replicate the use. As I said, most people will load it flat. If I did an uncertainty analysis overall, is this a be-all, end-all with an 0.12% error? Well, for references in a cal machine, this is pretty high. In the field, if we're looking at a 1% test machine overall, and then you get a combined error of 0.1, if we look at this same 10,000 pound cell, 0.1%, 0.14, and you're doing a 1% device, field use, not so much significant. In a cal machine where you want something, or if you're doing 0.1, it is significant. So take what you will with all of that, and do with what is. You can make it better. Not one of the larger errors, but it very, very repeatable. These adapters that we have can be machine flat, so you can use them for thread loading if you want to. Compression, tension, all of that. And by the way, these adapters, they all replicate what I was saying. 5/8 of an inch, it's 5/8 deep. So cable length, question earlier, which I wanted to answer. Oh, so I did have, yeah, I'll answer that for James. I looked over and saw it. Is there a training class? The newsletter came out today, and Morehouse, sorry. our newsletter came out today, which did announce the training. If you are not signed up for it, I'm going to give you, I'm going to put the link in the training. So there is an in-person training. We will use equipment. We will do one-on-one. We go 8:30 to 12. We have lunch. We go to 4:30 each day. People usually stay around. We'll have one day where the group will go out to dinner. All of us will pay for dinner. We'll have some drinks. If you drink, if you don't drink, that's cool. You can all. But there was the last class. It was 2 years ago. We're in the training room. We're using machines. This is September 10th through 12th. We do this like once a year or every other year, depending on demand. Sometimes we get a lot of people. People have been asking, so we certainly would love to have you come if you can. So thanks for that. Thanks for that question. Oh, and I want to put that, sorry, I wanted to put that in the for sure, put that in the chat. And if you're not signed up to our newsletters, please consider doing that. We try to be educational as far as the newsletter goes. If you see well, that's nice. I might have to pull my here. I'll just pull my Outlook. I don't think it's a big deal over here. I'll slide this over. And I'll anytime I do this. But we try to be, there's a sample on our newsletter here, new Cal Lab process. We just did a 6600 machine. We'll come to NCSLI. And then we get to why choose some of the things, but lots of times there's at least one or two educational pieces in the newsletter, or something we've done as far as making better measurements or something we found or recommendations. So yeah, thanks for that. Okay, so another question, is the effective thread loading area as important on column and multi-column cells as shear web load cells? Yeah, and loading, great question. That's it is. It is, whether you load through the base, whether you load through the threads. I said earlier, like the Honeywell, I think Model 41 actually performs brilliantly if you load it through the threads, not so brilliant if you load it flat. So there is, I know it's Model 37, sorry. There is differences, and it just takes time to like know. If the customer tells you what they're doing, it's so much easier as a lab. Like, I'm going to load it flat. I'm going to load it through the threads. Do you have the adapters used? Do you know what engagement? But yeah, there's different, the design of the cells, when you have internal threads, there is a difference. Now, column load cells, specifically single column load cells, that was that Sensitech cell. That was a pretty large difference. Multi-column load cells, how they're compensated, where you're engaging. Yeah, there's differences all around. There's no way around it. I was going to try to give you some numbers, but I'm not even going to do it because every load cell is different. Every capacity is different. You would like to think that you proportionally made them the same, but we don't do that. And then you get into the fact that your RT, yeah, no, they're all different. So that's good. No, good. Thanks for the questions, the training. Thanks for that. Sure, for that question. Sure. And I'll keep monitoring the window. We had one question here, which is better, 4 or 6 wire connections on load cells. So load cells used with meters that have 4 wire are subject to additional errors that the 6 wire cells are not. It's because voltage drop over cable lengths and the effective thermal span of the load cells can alter cable resistance. And typically we're measuring that cable resistance, unless we're using current milliamp, which I don't know enough about milliamp on that to give you some good numbers on that. But I can tell you when we're using ratiometric millivolt per volt, substitution of a 4-wire cable at a given length with another 4-wire cable of different length will produce additional errors. When I said I don't know enough about current and milliamp, my assumption is that it's not going to be impactful, though, until you take a 5-foot run of cable against a 100-foot run. I don't know. The extreme short, not variable like this is for sure, if somebody was wondering. But I amplifiers in general, which we haven't talked about. If you're doing 0 to 10 volt DC, or if you're doing 0 to 20 milliamp, amplifiers in general have a lot of noise, and resolving digits tend to be problematic. They're just noisy as can be, and they're nowhere near as good as the other systems. I get why people use them, but the ones that we see come in, our regular systems are so much better. So substitution of a 4-wire cable at a given length with another 4-wire cable at a different length will produce calibration will be required. Some recommendations. There are a lot of 4-wire systems out there that people like. ADMET Gauge Buster, which we have our own Morehouse Gauge Buster. It's ADMET rebranded because people like the smaller form factor, make no qualms or hide that at all. It's a good device. It's a 4-wire device. So what you see happening is people like this because you can program multiple points. You can do this. You have a freeze cable if you're doing machines. So your testing machine reads 2000. You put the freeze cable. You record what it means. Get it. If you change cables on that, which we have one customer that does, they send us a 20-foot cable one year and a 10-foot cable the next year, and then their change from previous never meets the stability requirements for ASTM because of the change. It's problematic. So the recommendation, if you're using a 4-wire system, is basically that you put serial numbers on the cable, and you make note that you only want to use that one cable. Some people have made 2 or 3 of the same cable, of the exact same cable, like you use a Belden cable or whatever. That's fine. If you want a backup cable that you've made at the same time, more power to you. We highly recommend serial numbering them and marrying to them. Your other issue though, then, even if you've covered your rear, is operating at different temperature will change the resistance, which will cause a voltage drop. Is this really that big of a deal? Someone might ask. No, not really. But it is something to consider. It's another variable that's out there on the temperature change in the 4-wire versus 6-wire. The length is huge. The change in length of the cables is just a gigantic impact from going to 6-foot to 10-foot. Is going to give you some large errors, and I have a slide on that. But the reason is the cable response to temperature change affects the thermal span to the load cell. 6-wire, you're running sense wires, it eliminates it. And then 4-wire, there will be an impact. The sense lines are separate from the excitation, and basically what this does is that it eliminates most of the impact due to variations in lead resistance, and it allows for longer cable runs in outdoor and extreme temperatures. I don't think many people are in extreme temperatures. The most I ever hear is like pipe testers in the dead of winter that are 2% devices anyway, where icicles are hanging on everything. But who knows? Someone might be in the Arctic doing something. Um, so any cable, somebody might ask you, wire cable. Most load cells are 4-wire by nature. There's nothing really special to them. If you see a load cell that's 6-wire, usually what that means is somebody has the pins A, B, C, D. This is our cell, E and F. I know my alphabet, right? So if something like this, A is excitation. Internally, if you pull that connector apart, you'll probably see like a little wire that jumps A to E, and or yeah, D to E, and A to F, and then there's D, and then there's E. If we're looking at systems, what I'm basically saying, these are my wiring pins for drawing with a mouse. What we're basically saying here is that you can run it on the cable side, you could run it internal. I would not pry a connector off a load cell. They are nitrogen purged and whatnot. So I would just run the cable. Any 4-wire load cell can be used on a 6-wire meter, and you can use the sensing function rather easily by just pairing the excitation, positive excitation with positive sense. on your cable run, if that makes sense. So the way you signal lines B and C just run to whatever connector you need to run to, and then you double up your excitation. You put you double up. So you put two wires on. I don't know why this is doing this, but two wires on A and two wires on D. So D would get positive. D would get negative excitation, and your negative sense line would be run on the same line. Absolutely no problem to do this. It will work. It's very easy. Why in the world would I, not use 6-wire? I don't, like I said, you like your indicator for some reason. And what we did in class, one time when we had in-person training, which we'll never do again because it was the most futile exercise in boredom, is we basically warmed up a load cell, used a 6-wire cable, and then we used a 4-wire cable in the same load cell, waited 10 minutes for that to warm up. We kind of cycled that. And then we we took that 10-foot cable out, and then we did the same test with 6-foot cables. The one with sense absolutely agreed within like 10 parts per million. The one that was 4-wire varied by about 0.106%. And then I typed this in an uncertainty sheet and showed people that a cell going out the door where the expected performance is about 0.4.5 pounds became 12 rather quickly. So sense is a big deal in that aspect of swapping cables. It certainly ruined the one customer stability for year to year. We try to work with them and say just serial number your cable and keep them. If you use the long cable for everything, they didn't want to do that, so they continually have problems. Other error sources, I like this one, 5 volts versus 10 volts. This is a tough one. And when I say I like it because it's the same meter. So right here, we use the exact same meter, Morehouse 4215, and basically just said, I'm going to do 5-volt excitation, and then I'm going to do a 10-volt excitation, and I'm going to plot the difference. So the variability is only internally to the meter. Now, different load cells will respond a little bit depending on the voltage change, but in general, 1% is not a bad number. You talk to different people. I prefer to operate at 5 volts, the lower voltage, because of thermal effects, and I get a little bit. And when I do that, I get a little more resolution, which I wouldn't be that excited about that little more resolution, though overall, not not a huge difference, but E74 in the reporting criteria says you must report excitation and wavelength. So just figure out what you want to do. Our Hatties that go to a computer that everybody loves, they operate about 5-volt excitation on load cells, and we get really good results on it. Tare loads, if you have a Cal machine, I get this question a lot. How much Tare load? Some manufacturers will say 1% of capacity for the load cell. Some will say 2. I'm on the 2. Some of the testing I've done, if we look at this number, Tare of 2%, which basically means I have a 10,000 pound load cell and I put 200 pounds on it and push the Tare button. So it's like I stuck it in a machine. And when I see numbers going high and low, and I consistently see a mash of numbers, I don't think there's much impact between Tare and no Tare as far as this. This is well within the uncertainty of the machine. Now, typically, I did say if you caught it earlier, most load cells will get some in good machines will get repeatability characteristics of about 7 to 10 parts per million. So regardless, the number is really low. I'm very comfortable telling people with a shear web load cell that if you don't exceed 2% of the capacity, meaning if a Cal machine, 100K Cal machine weighs the Tare's 500 pounds, 50,000 pound, 1%, 25,000 pound, 2%, no problem. 10,000 pound load cell with a 500-pound tear, you're at 5%. You're going to have some additional error. And as soon as you start tearing out more numbers, and different load cells will act differently for this. So, general rule of thumb is 1 to 2% of the load cell capacity for your tear weight, and you're fine. Overshooting a test point, well, if you get the automation, this doesn't happen. But what I did here was just, I get this question, like, what if I'm operating a machine? We have a UCM, and as a technician, I overshoot the test point. We've all done it. It's slow and methodical to try to creep up on that point, and sometimes you think you can do it, you hit the button, and it overshoots the point, the hydraulics shoot up, whatnot. So this is just basically saying, look, if I overshoot 2% of capacity, and I did numerous tests on this. I'm getting like not a big deal whatsoever. As soon as I get to like that 4%, 6%, and 10%, I probably should start my run over, depending on what you think and what you do. At 4%, depending on what I'm calibrating, if I'm calibrating a dynamometer or dynafor, I'm not restarting. I'm not restarting at a 6% overshoot on a device that's reading to 0.1% of full scale. Though at some point, I do want to consider it. If I'm calibrating another customer's load cell, if I'm above 2%, I really should restart my run. And when I compare data, and this alone, when people do their uncertainties, when they do their R&Rs, you see this a lot between technicians, and you can spot it in the data because the repeatability numbers, they probably overshot the point. When I initially go over this and with people, I say, well, how'd you do repeatability? Well, I did this. I said, you overshoot the point. I may have. I said, can you get to like, you know, 4,900 pretty well? Yeah, I can do that. And then can you creep up to 5,000 and send over some different numbers? And they do that, and then everything comes in, and they get within the 003, or they get within the 0.203%. The automated cow machine, you don't need to worry about that at all, because the automation is better than any of us. It'll just hold that force all day long to within like 002, 001. In our 1,000,000-pound machine, our tech always says, I'm holding to 5 pounds. It's like, meaning the automation is holding to 5 pounds. So is what we did this test for, and there's really, if we look at expanded uncertainty, combined uncertainty, and overshooting a test point, and we kind of say, what's the additional error? Overshooting at 2% gave me about a 4 part per million error. I kind of would ignore that on most any calibration I do in a UCM. After that, like I said, maybe restart the run. So there, my son created that one, automated machine about overshooting test points. Look, the automated UCM, it controls the force well better than technicians. Your R&Rs become better. Your repeatability comes better. The technician sets the load cell up in the machine. The machine just runs. They go rotate it if they're doing E74. They do whatever else. They can set up, warm up another thing. They can run data. What's happening in our industry is basically, and I think any company knows this, is technicians are hard to find. Most people are probably resorting to training programs, in-house training programs. Sometimes when technicians are trained, they leave to go down somewhere else or whatever. This is where you work on culture, values, management, all the other stuff. And we have other courses on that. It's something I'm passionate about, at least, is creating that culture that thrives innovation and that thrives promoting the positive customer experience. Anyway, from that, the automated cow machine makes life so much easier for technicians and gives you better results. I would say I was pretty good at chasing force points, but I'm nowhere near as good as that automation. So other error sources, time differences. If one lab's doing 6 seconds and the next lab's doing 30, and then you have the drift with calibrations with time. So a good point. You also want to be careful when determining pinout because of the mirror effect. Different manufacturers, pin pinouts at different reference points, and some don't match. Yeah, I wish everybody that Elliot, that's a great point. Western Regional is the convention, which is ADBC, A and D for excitation, B and C for signal, and manufacturers go all over the place with their pinouts and stuff. Why we couldn't standardize? If you come to our lab, I will open our file cabinet. We have hundreds of cables. They're all labeled by code. A code is a certain pin, and then we have like A1, A2. We use different letters for the type of actual connector, and then we do 1, 2 up to I don't think any go beyond 100. I don't think any go beyond like 30 of the different ones. But yeah, people make the different ones. They use these other things. People send stuff in all the time, load cells. So it's so much easier for our system to have a file cabinet and say, go grab cable B22, and then guess what's on cable B22? The wiring and the pinout. Now, if you didn't have that, you could chase things, and it's just one of the tips that we've done that's made life. Though my biggest complaint is that why in the world do we have hundreds of cables in our filing cabinets in our lab? Because we couldn't standardize. And I was like, why do we have blocks that are Swiss cheese? So getting into all of this, why is all this important if you have these biases and uncertainty? And if you just look at things, now this is specific risk again, not the diatribe, but if you look at things like calibration capability, measurement capability index, TUR, test uncertainty ratio, 20 to 1 versus 1 to 1, 10,000-pound load cell, measured value 10,000. We're saying the specification, someone wanted an O5, which is very doable in a dead weight, very doable in most machines. Looking at these uncertainties and looking at risk, so when you're doing this in dead weight, assuming the instrument has good resolution versus the other machine, risk 20.83. What this does is basically says, hey, the lower I can get the uncertainty, the more I can get these adapters and everything else correct, the more room I have to pass instruments. And the better my lab's going to be, because I'm going to give customers lower uncertainties. I'm going to tighten up my processes such so I know when I tell somebody their instrument's good, I have confidence in our technicians, our process, our quality system, whatever it is, that when we are adjusting something, we're adjusting because we probably know it's bad. Now, the benefit of low TURs is that you're adjusting less and you're making less bad decisions, right? So what that basically means is when I have a small uncertainty, my acceptance limit is large, and when I have a low uncertainty, my acceptance limit is quite small. And I always liken this to thinking about that. We just went to a concert last weekend, Nickelback, if you're wondering, Nickelback and Travis Tritt, interesting combo, but they both were good. If I'm tailgating at a concert, I like this space, right? I can put a lawn chair out. I can put my cooler out. I'm not going to bump into the car beside me. This is the impact of having a large TUR, right? I'm just not, versus a low TUR, now it's winter time. These cars look pretty clean because they're ritzy, and neither one is my car. It's somebody that attended my class and said, this is what I have to deal with every day getting out of my car. I think it would be good because you showed me that large parking space to have the small parking space. I can't even open my car door. I have to shimmy out. I have to suck in my stomach so it doesn't touch the other door. This is, and the chances of what's one of my concerns when I walk out, that I get a dent in my car. So because someone beside me just swings open their door or has a kid or whatnot. We've all been there. Why does this all matter? And going over some things as we wrap up. Look, bridges, like right here's gusset plates, NTSB, the two-thing gusset plates. This is Minnesota. Lots of people died. Was this ever tested? Was it ever spec'd? Did they do the analysis? So many questions over and over. If we get it right, so we want to choose that right equipment. We want to understand what I'm showing you, the guard banding, which is the small uncertainties give us more room to be in, and we want to understand that manufacturers don't get it. A lot of them just don't. They'll set the resolution equal to the tolerance, which is a bad thing. So in our world, if we want good force equipment, We went through the load cells, we went through the indicators, we went through the errors. If we want good equipment, if you want to make equipment or buy equipment, we want equipment that is plumb, level, square, rigid, free to torsion. All these things are going to be problematic. So plumb, exactly vertical or true, it's impossible to be exact, but there's an automated machine. We stack the weights, large weights. Older machines, we didn't do this. We learned our lesson, physics principle, larger weights on top, smaller on the bottom. It's a pendulum. You think about it, a long, our one engineer calls this a stringer. I call it a yoke. Whatever, the way this machine's designed is such that the smaller weights, you can do a visually simulate smaller weight angle. It's basic physics. You probably had it in 9th or 10th grade. Um, Level, right? These machines have levels. The setup, the better you can level it on a flat pad, the concrete, if you're using steel, preferably, you can level all these machines. You're going to be happier the more you can do it. We do ship it with a bubble level. Probably that gets you close. Get a machinist level, get a digital level, get something else. Level this as best you can. You will get better results, and we certainly allow that too with the adjustment in the feet. Rigid. So scale press, this is a redesigned scale press. There's I-beams, reinforced stuff in here everywhere. There is so much steel in here as far as reinforcement. This thing, everything bends. Our original machine did have some visible flex to it. I do not see visible flex, but under a microscope, you can almost detect anything. If I push on my desk under a microscope, it looks like something chaotic is happening and things are deforming and whatnot. Torsion, one of the biggest error sources in force is everything tends to want to twist, right? So we want to free that as much as possible. ISO does a good job with the sphericals. If you're out there doing field cals and you have balls and sphericals like the stuff that Lloyd makes, that's great. I can't say enough about them, because that you'll still have some torsion when you go to pull on something, but it's not going to be as significant. When we first started and built the PCM, our first numbers were atrocious. They were like 0.1%. And I said, we can't sell this. And then we did a bunch of stuff. It's in the manual about adding bearings, adding sphericals, doing all this other stuff. And we got that error down to less than 0.15% or 0.2. And it took a long time to remove that just torsion error in the top here. So if you have a frame from like Harbor Freight or something, chances of you having torsion are very high. It needs tested, and that's where proficiency test and everything else come in. Replicating field use. This is my plug again for ISO. I keep saying it, ISO 376. This machine really doesn't replicate field use if you do compression and tension in the same setup. In fact, ISO says that they should 376 separate setups. Most machines, there's a separate setup for tension and compression. It can replicate field use, but you have to unscrew this and make a different compression setup, which guess what? Most people don't do. So there's just different equipment from different NMIs. This is the big NIST machine, 1,000,000 with weights. There's one of our machines that was sold. I think this is Vietnam that it was sold to, but yeah. And there's another machine. There's a GTM machine. It's cool looking. It's yellow. They have really cool engineering. But yeah, to replicate field use, should not perform compression and tension in the same setup. It's common practice. They should use the customer's top blocks. I mean, if you're using a machine like this, how do you use the customer's top blocks? Require a base plate to load against, and calibrating for 75. They should always use the adapters recommended. ISO says, I mean, I can't say enough about it. The reference equipment chosen will affect your ability to issue the conformity statement. Here's this. As the increasing uncertainty, you just get less of a conformance zone. And why this matters, there's a cost. It's in Quality Mag. If you don't subscribe to Quality Mag, it's good to read it. Greg Senker and I did this paper. It's called "The Definition of a Fool is a Drowning Man Who Tries to Keep a keep it a secret. A story on purchasing the wrong equipment and keeping it, people will do this. And what this graph or what this chart is basically showing you, to explain it, and you can read the article, you can look at our decision rules paper, is if I spend, and I'll round this off, 20 grand to buy a Fluke 85, 80, yeah, 85, 88. I think the 80, yeah. If I spend that money to buy that versus buying some low end meter that management says is okay, if I'm doing enough work down here, this is an example. We were just measuring resistors, speaking about simulators. This is a resistor example. It's in JCGM, one of their examples, and they're using we kind of took their example and put dollars to it. So if I'm testing all these items, and I'm using this cheap instrument where I'm only 1.44 better, I'm going to falsely accept, the math doesn't lie. I'm going to falsely accept with the tolerances that we're staying 1,000, and I'm going to falsely reject 23,000. Our production cost, or your calibration cost, if you think about it per the lab view, stays the same, right? As far as if somebody pays me for a calibration, you might have adjustment criteria, but just say somebody pays you a flat fee for the calibration, or you're making this resistor widget. It's going to cost us the same on that side of things. If I false reject it, which means I say it's bad when it's actually good, what are you going to do? You're going to adjust it and send it to the customer. That adjustment costs money. If it's false, then you're going to send them bad. This is a production example, so we're rejecting resistors here. I've rejected enough resistors that it's costing me $323,000 per month. My cost now, I made something, I'm gonna want to retest it. That's costing me 838,000. So if I buy the better equipment, my production cost, false reject and test is 1.35 million. If I buy the low end equipment, my cost is 2.51 million. That is a difference of like $1.2 million if it's monthly, and multiply that out. And the reason I'm explaining this and doing a bit of word salad with it is, if you can envision this scenario, how many people in the world are doing this and they don't know it? They're rejecting good product, and amplify that out by every industry that you know of. We're talking trillions of dollars, like stupid amounts of money, where if the company, and you guys are, it's late in the day, but you can do math, the extra cost on this indicator, if we just say it's 5 and 20 grand, 15 for $15,000 more, the company could save about $1.2 million a month, and they don't do it. And they don't realize they could do it. And there's a lot of small shops, there's a lot of Cal Labs, there's a lot of other people that are out there that are in this same scenario where they're not buying the right equipment. They're buying the $30 SB on Amazon, they're buying the cheapest meter, they're buying something that says it's TEDS enabled, and they're not ever quantifying that additional error, and they're testing all of this stuff that's out there, and it's costing an absolute fortune. So, and with some funny stuff, this is marketing material I love, and picking on Intercomp. This is still on their website. I'm going to pick on them until they take it down. Our customer loved the precision that they get with this instrument. Anybody that making a torque measurement that think this is a good way to measure torque, likely not. But if you want to do the math, you can kind of calculate here the degrees here, and assuming 45 degrees, someone might say it's 30 degrees. The math comes out to about a 29% error. If the marketing department would have put this at 90 degrees, I would never put this slide in here and never make fun of it, because there are problems with length, obviously, but this is by far a gross one of those gross examples that if somebody's actually testing this as a way to measure torque and 29% error is good enough, I don't believe it. Showed you this earlier about not following the standard. Know the standards, know what you're doing. So we do this. I have a little bit of a true and false for everybody as we wrap up, and then I'm happy to answer any questions that you have them. I know we went 15 minutes over. I was watching the time. I could have sped up to do it, and there's a lot of stuff here but choosing a readout with good enough resolution, I kind of did that in Excel a little bit. But then none of it matters if you're going to a cal provider or you're that cal provider that bought the cheapest stuff that doesn't have the high enough test uncertainty ratios or measurement capability index to say something's good when it's good and bad when it's bad. So and if they don't follow published standards, it's not good. So let's play along. I up for true, false, or whatever, but pin size on a tension link can affect output. So true, right? Remember the ED extreme, the pin size, the 1.72% error on the 50,000 pound device. And then I showed you the 13 out of 24 measurements were not in just by rotating the pins. The flatness of the bottom adapter can affect the reproducibility of the load cell. That was the multi-column cell example, where when I grounded and used a flatter base, the number went from like 0.123 to 0.023. A 1 million pound column load cell will typically weigh less than 50 pounds. And then I got pounds wrong again. So that's a pretty big load cell with 4-inch thread, probably not going to weigh under 50 pounds. That would be but again, I should have clarified that with the tension or compression. Though a column load cell, not multi-column, will can weigh a lot less than a shear web. Most button load cells achieve better than 0.5% of full-scale reproducibility. That one's a little tricky because it is false, though, with the caveat that if you put in the adapters that we have and stuff, I showed that you could achieve about 0.2%, but in general, without the rate adapters, no way. It was about 1%. Okay, so repeatability can be improved by taking more measurements. Didn't really cover this. Some people say, and when you get into uncertainty, you'll want to look at that. It certainly is recommended that you take more measurements for your repeatability because one or two aren't going to give you enough. But generally, this is a better rule of thumb to take more measurements. So I apologize. I didn't cover that one as well as I wanted to. What load cells are more sensitive to off-axis loading? And that is, remember the thing, S-beam, button, single column. This is a all of the above answer. So best practices, you have this in your notes, some of the do's and don'ts. I yesterday asked AI I put my slide deck in AI and it came up with this slide and then I edited. I said, yeah, it's pretty good. Pretty good slide to do it, but it had two things wrong. AI still will get things wrong as far as things go, but pretty good there. So think about this. If you have any comments, I'm happy to answer questions. If you want to shoot anything over, things that could be better, suggestions for improvement, always happy to hear them. Happy to hear feedback, negative, positive, whatever. Whatever you want to say, it was your time that you sat here with me. Most of you held on. We had some drop off. Most of you held on for it. So your time is valuable, and I thank you for that. But now you've made it to the end. You should at least have a good thought on why measurements matter, what to ask your calibration provider about, like, hey, and what your calibration provider should be asking you, best practices for calibration success, the top varying blocks, doing this, how to improve your own process. And now I just leave with, what will you change tomorrow with this? The 42 of you that are left, like, what are you going to take away? We spent all this time together. What are you going to implement to help us create a safer world today, to ask better questions, demand better calibration, and follow the standards? Because that's where we all need to get to. We learn together. The questions that you gave me today were absolutely excellent. I appreciate them. I love when people are doing this. We're online and virtual. That's a lot harder than in class to say, ask and go to the whiteboard and do all this other stuff. I can pull out OneNote if I need to. I didn't have to today. You asked me stuff that was we were going to talk about. Other things I highly recommend for people: ASQ, Metrology Handbook. We've written 2 chapters, so yes, I am biased. I've written 2 and edited 1. Highly biased on that. I think it's a great book. Even Better book, I have nothing to do with this. The Even Better book is the one in the center, and that's Introductions to Statistics and Metrology. I think this has simplified things for me over my 25-year career. I wish I had this book 25 years ago. It is excellent. It explains concepts on uncertainty and statistics in a way that people can understand them. You can get, I believe, digital copies. I have a copy at work. I have a copy on my desk. I think they're like $100 on Amazon. Highly recommend it. I get nothing for recommended it. I do know the folks. They're at Sandia, and they're awesome people. And they also have a program called SunCal, which is free. Colin is a remarkable asset to our field of metrology, the second guy listed there. So always kudos to him. If you can take an uncertainty class that he offers at NCSLI or somewhere else, I highly encourage you to do it. I've sat through them, numerous ones. I've had him sit in my classes. Excellent person. And that's it. We have YouTube videos. Follow us on LinkedIn if you're not. I appreciate that, and take advantage of our downloads and whatever other books that we have. Free training library, the documents, and then that continued training. Started with that. If you like this, if you want to get to that point where, I know there were a percentage of advanced, but you beginners, that large percentage of beginners, you want to get to a point where you're more advanced and you know this stuff, sign up for the email. It doesn't hurt. You can ignore it if you don't, if your day's busy, and get to it. But 10 minutes a day over the course of 42 weeks, guarantee you'll start implementing some of that stuff if you're motivated to change. You have to be motivated. So